Hi, good morning. So it's just coming up to 8 a.m. UK time or 8 a.m. London time, and every week we like to do this webinar for the ZP Developer Zone members. So I put this slide up every week, but it's just a quick summary of who we are and what we do. So this is the ZP Developer Zone. ZP Developer Zone is a group, is a club of people who are interested in the development or in developing biosensors for many applications. And every week we kind of do a webinar specifically aimed at our developers. Now, as part of this kind of this work that we do with the community, there's the ZP Academy, where you can find free courses. We have the ZP Developer Zone website. We do post jobs on the website, and we also have collaborations. We still have one of the ZP Developer Zone members in the UK at the moment, and we're arranging other collaborations as well. So I'm just saying hi to one of the members. So let me just sort of dive into it a little bit. Now, what drives these webinars every week is we have a forum, and if we get sort of questions in, questions come in, they get posted on the forum. Now, we had a couple of questions this week, and I actually think that one of the forum members is one of the best people to actually cool. One of the forum members is actually one of the best guys to answer this question. And actually, I've just seen Aftab pop up online as well. And actually, when I think about it, he's also one of the best people to answer this question. But let's have a look at the forum questions for this week. So we had one of them was about, how do I make a CGM? How do I make electronics for CGM? So how do I make electronics for a wearable continuous glucose monitor? And we also had a question from Census, which is in Uppsala. And they're busy making a biosensor on one of the hypervalue carbon electrodes. So they also sent us some questions this week. So let's first of all take a look at the questions. So if I kind of paraphrase what they've said, they've got some of the carbon hypervalue electrodes from ZP, and they're trying to do electrode deposition of nanoparticles onto the surface of gold nanoparticles. And then they're trying to put a linker molecule where they essentially have a sort of organic molecule that one end sticks to the gold and one end then has its NH2 bond, and then you use that kind of NH2 to do what you call an EDC NHS coupling, so they can then couple like an antibody. So they have a carbon surface, they want to electrode deposit some gold nanoparticles onto the surface, and then they want to put a linker molecule onto the gold, and then they want to couple the antibody onto that. So it's fairly standard stuff, and they're having a few problems. Now, if I read the problems, essentially one of the problems they've got is they've only got 1 in 3 of them is actually working. So that's a 33% yield. I was actually talking to a manufacturing engineer who I very much respect, and we were talking about, we're on a program together, he's a consulting and we're consulting, and he said, oh, you've got a yield of 33%. We were talking about another project. He said, oh, that's high. So I just want to put things into context a little bit. There's a false, incorrect understanding that when you're doing R&D, that your manufacturing yield is going to be high. It's not going to be high. I mean, it's probably worth saying that, in order for us to make a biosensor, we put them in between 111 hours, to something like 10,000 hours. So, I imagine that this group is probably put in the 111 hours, but I don't think they've got anywhere near the 10,000 hours. So don't be, cool, Hitcher Monsieur. Cool. So don't be disheartened if your yield is low, if you're working with university equipment in a university lab, where the environment's quite uncontrolled, you don't have quality systems in place, you probably don't have a clean room environment in order to do this work. You're just making best use of what's around you. So I had a professional, manufacturing engineer when we were talking about a particular product that we were on. He was impressed that we actually had a 33% manufacturing yield. And it's exactly what you've reported. So don't be too hard on yourselves, would be one of my comments. Now, what I would say is this, that this I'm going to not quite answer your question, but I'm going to answer your question in another way. Whenever I see that, now that I understand the chemistry a bit better, whenever I see the idea that somebody is going to take like something like a carbon surface, or maybe some other surface, and make electrode deposition upon it to make a, in this case sometimes they just do electrode deposition to make a gold surface, or in your case you're just doing sort of partial electrode deposition to make nanoparticles. Now what that says to me is you might as well just start it. Unfortunately it's too late now, because I know that you've kind of committed, but just start with a gold electrode, because in manufacturing terms, we want to make things as simple as possible. So you've got a process where you have a carbon electrode, you electrode deposit gold nanoparticles onto it. So that's essentially, that's a single, you have a step of processing there. To make that actually, more manufacturable, you would just start with a gold electrode, and I would ignore the whole thing about, oh well, gold's expensive. Processes are expensive. Processes of getting gold ore rate and electrode depositing it down and checking everything's good. Cool, Philip is here. That's expensive. So if any of you are in a situation where you think you're going to have, let's say, gold, and then you're going to couple your antibody to gold, rather than going carbon, gold nanoparticles, and then linking, just go gold electrodes. Because you make your life simpler, and if you make your life simpler, you're essentially making it more manufacturable. And the cost that you're saving in terms of not having a pure gold electrode is really offset by the fact that you have this extra manufacturing step in your manufacturing process. Now, I know for this particular group it's too late, but I just want to kind of, not too late, but I just kind of you've made your decisions and you're correct, just move on with them, it's fine. But I just want to make sure that people generally understand that rather than making gold nanoparticles on top of carbon surfaces, we just recommend just going straight for gold. We have had projects coming in the past where it was a carbon surface and we put an organic molecule on top of that, and then we were going to complex a gold nanoparticle on top of that, and then we we're going to complex another molecule on top of that. No, it's just too many processes. Each process will lead to variability, which is in part your yield thing that you're talking about here. You're saying, I'm only getting a 33% yield. So if you, let's say the 67% loss in materials due to that first process of electroplating gold onto carbon, you could make that step 100% yield by just buying gold electrodes. So I think I've said the point enough. And of course, Hasim's seen this data, and Philippe has seen this data, and Aftab has seen this data, all the guys who come on regularly. This is gold electrodes. This is our gold electrodes used to make a antibody immunosensor, and they work really well. As Hasim said a couple of weeks ago, great looking data. So for anyone going forward, don't electroplate gold nanoparticles onto carbon. It's not worth the hassle. Just go straight for gold electrodes. Now, if you are on a carbon electrodes, there is a good paper out there. It's not a good paper because I'm an author on it, but we use this paper quite a bit in our own work, and we know it works really well with the hypervalue carbon electrodes. So this is what we're doing. We're taking this is the hypervalue carbon electrode that we use and we promote a lot. And now I'm not going to try and tell you that this is the world's most amazing data, but this is the actual concentration versus what we've predicted the concentration would be from our calculations. So this is essentially, we've tested these concentrations and then we've put them through a model and seen how good we correlate with that model. And so you can see, you can see that there's some spread in the data, but you can also see that we do have a strong trend. So it does tell us, and now to get that kind of correlation, we had to put something like 111 hours worth of effort in there. So it does tell me that we can take these carbon electrodes, we follow the paper that I just referenced, and we can get some pretty, well, we can get a good correlation. I wouldn't say it was excellent, but we can get a good, in fact the R squared there is about 0.89. So we can get good correlation. Now let me tell you how we do this kind of work. First of all, read the paper, and then we essentially start a workflow where we kind of have 60, I say sensors here, I should say 60 electrodes. So we have quite a large batch of electrodes, and now we do test them. Now, when I say test them, we kind of check them by cyclovoltammetry. Now, I think that's less important, to be frank, when you're using ZP electrodes, because we've already tested them in our factory to make sure that they were good before they shipped. But we take these screen printed electrodes, we test them, make sure that they're all, let's say, good and within specification. We then rinse them and we dispense. And what we then dispense onto them is a pyrene NHS linker. So it's a pyrene is a sort of planar molecule. It's 4 benzene rings, and these 4 benzene rings here are really good at binding to carbon surfaces, because carbon is in some ways is graphite. There's a lot of aromatic or benzene rings, and so these benzene rings stack well on top of these other benzene rings. But sticking out of this pyrene molecule is an NHS linker. So it's very similar to what the guys are trying to do in Uppsala, except they're trying to link, they're essentially trying to finish with a NHS type linker as well. But we've really skipped the steps. We've just gone carbon, pyrene, it has an NHS linker on it, and that will allow us to bond straight to the antibody. Now what we do is we put the linker on there and we test them. So I'm just showing you our workflow. We take 60 electrodes, we make sure they're good, we dispense the linker on them, we test them by cyclovoltammetry. Then we rinse. We've essentially sacrificed some electrodes here. So we've kind of sacrificed 3 electrodes here just to do the testing. And then we carry the other 57 forward. And now on the other 57, we actually put down the antibody. And then we test that. So we've sacrificed another 3 electrodes. So you can see this is a real sort of manufacturing. Hey, Dima. So you can see that this is a real manufacturing kind of process where we functionalize, we test, we take the batch forward, we functionalize, we test, we take the batch forward. So all the time, these 60 sensors that we originally started with are getting attrition, because we're losing sensors because of the testing all the time. But this is the way, essentially real manufacturing runs. So we put the linker down, then we put the antibody down, then we put the BSA blocker down, and we test to make sure that's worked. And now we're ready to start putting antigen down, and we test, and then we increase the concentration of antigen, and we test, and we increase the concentration of antigen, and we test. Maybe this is a bit extreme, and we put the antigen down and we test. So we get quite an attrition of electrodes, because you can see that there's 60 minus 3 minus 3 minus 3. That takes you down to about 51, and then we're left with 3, 6, 9, 12, and then we need 12 to kind of finish the job. So we start off with quite high numbers of electrodes and bring them through the process all the time, losing them because we're actually using them to test. Now, I don't know if Shirley's online today, but Shirley's one of our very, very smart engineers, and I realized that what we could do eventually is actually put this workflow into Julie. So we have at ZP, what is it we do? We do contract development and contract manufacturing of biosensors, and then it's just as part of a service to the community, we have these webinars, and we sort of give you, the developers, an insight into what we do. Obviously, what we're hoping is that one day, you'll either come and work with us or you'll manufacture with us, but there'll be some sort of long-term relationship. And that's why, we're willing to come and do this. But it just gives you a sense of, the workflows that we have and the functionalization and testing that we do all the way along the workflow, and actually the numbers of electrodes that we need going into these kind of tests. And that's why I do encourage people to do the hyper value carbon electrode, because this can get really expensive if you go for more expensive screen printed electrodes. I do have a lot of people pushing on me to do a hyper value gold electrode. I just need the first person to say I will place that that order with you, and then we'll make them. Because I do realize that in order to do biosensor development, you need quite a lot of electrodes. Quite a lot of electrodes can be quite expensive, and we are sensitive to that. So we have a low cost carbon source. We could probably do it in gold as well. We just need to kind of find the first person who says, yeah, all right, I really need to buy them. So I didn't answer the question that the guys really asked, but I did say this: don't be too disappointed with your yield. If you want to have more like an 80%, 90% yield, then probably put in 10,000 hours worth of effort. By the way, you haven't got 10,000 hours worth of effort, so in that case, kind of accept the yield as you are. For people going forward, I wouldn't. The number of processes you can get out of your overall manufacturing, that's good. You don't want to put complexity into manufacturing, because every step in manufacturing is a loss of yield. So I could immediately increase these guys' yield by just changing from the carbon electrode to the gold electrode. And then for these guys, if they could, I'd like them to follow the paper that I referenced earlier on and follow our workflow. But of course, then it means they have to change their chemistry, or change the way they were going to do this. And I know it's hard to sort of change direction in the middle of a project. So maybe they could just write it up as a kind of alternative way of doing it. And it can be a little chapter in their thesis or their project. So let me just I'm going to just show you kind of. Also, maybe I can. This will help a little bit as well. I'm enough of a scientist to kind of know what I'm about to say. Can also be criticized, but I just want to give you a sense of the way we are analyzing immunosensors these days. Is we are analyzing them by. I don't think cyclovoltammetry works particularly well. I do think differential pulse voltammetry is not bad, and I think square wave voltammetry is pretty similar to DPV and differential pulse voltammetry and square wave voltammetry. They're pretty similar. I'm not sure if one's better than the other. You just try them both and see which one works. So cyclovoltammetry for immunosensors, I don't think works particularly well. We have had good success with square wave voltammetry and differential pulse voltammetry. I think Hasim, who's online today, has got quite a lot of experience with differential pulse voltammetry. But the technique that actually works the best, in my opinion now, for immunosensing work, is unfortunately impedance spectroscopy. Now, I think that the guys that asked the question, they don't have a board that could do EIS, but unfortunately, EIS is the best technique. Then the good thing about EISC is that when you do the technique and you put together your equivalent circuit, you end up with a circuit like this, but there's meaning to this circuit. This tells us our electrolyte variability or concentration or salt concentration. This component often tells us about our linker, and this molecule, this part of the circuit tells us about the antigen binding. So in this part of the circuit, there's three components. There's a capacitance, a phase angle, and a resistance. Now, the reason I bring that up is they don't really teach this at universities, but I think actually younger scientists are much more au fait with data science and using things like Python. I know Hasim has been recently learning Python. Now, the reason I bring it up is because when you look at any one of these signals, R3, Q1, or this angle, none of them look particularly good. But when we combine them into a single algorithm, we can actually get very good correlation. So I think that I will accept I'm not going to say cheating, but I will accept that, you know, if you use a lot of inputs into an equation, you can kind of fit anything. So I do accept that. But what I am also saying is, if you don't have brilliant data as part of your thesis, don't just look for one component in your signal and say that's got to be proportional to my concentration. No, that's the way you were taught at university, because, you know, I was taught by guys who were trained, you know, in the 70s. You know, data science was really not a thing then. Now, if you're taught by a guy that was trained, you know, in 2010, data science is a thing. So I would say get smarter with your data, because it's not taught to chemists, data science. I think it will be, but you can actually get some quite good. You can turn a bad sensor into you can turn an okay sensor into a great sensor using data science. You can also just be, you know, massaging it so it just looks good. But honestly, even with these guys, you've got to look for features within your data. The sum of all these features might actually give you a good, strong signal. So you've got to get a bit more. We put as much effort into data science these days as we do put into actual making biosensors. Right, question 2. Now, first of all, I have to apologize. I misread question 2, first of all. I read it as, I want to make microneedles for CGM, for continuous glucose monitoring. This is a question that's kind of close to my heart. You know, I like microneedles, I like continuous glucose monitoring, but then I realized he actually was asking a circuitry question. So I answered the question and then reread it and realized, oh, I've answered the wrong question. But let me do two-part answer. First of all, the question I thought I was answering. Now, I hope you guys, hi Naguan, hi, yeah. I hope you guys sort of appreciate this, because what I'm saying here is, when somebody comes to me and says, I want to make, like, you know, a CGM sensor, I want to put this as a case study up for you. And the case study is this. This is a company called Sano Health. They were based in the San Francisco area of California. They were making a microneedle array for doing CGM. I want you to know that I don't believe they've been successful, or, you know, the business has kind of undergone several iterations, but they've spent something like, or they've raised something like $20.65 million US. So they were making a wearable CGM sensor using microneedles. So they spent $20.65 million US doing this. Now, $20.65 US, that essentially translates to 111,000 person hours. 111,000 person hours. So if you work 24 hours a day, 7 days a week for 52 weeks a year, so basically you just did nothing, you didn't sleep, you literally didn't eat, you didn't do anything but work, you are capable of doing 8,765 hours a year. So that means that if you were to try and make something like they were trying to make on your own, and you work 24 hours for 365 days a year, then you would actually take 12 years. Now, if you did a more 8 hours a day effort, just no holidays, but 8 hours a day, it would take you 36 years. So it's a bit like the question earlier on, which is, the first question was, our yield is low, and my answer to it was, accept it sometimes, because actually it's a lot of hard work to make a good biosensor. Now, the question here is, how do I make a circuit, or an electronic circuit for CGM? Well, I'm going to give you some hints on it, but I also want you to know, when you ask these questions, people have spent tens of millions not being able to actually deliver this kind of stuff. So, you know, you've got to have some context about how hard the problem that you're trying to solve really is. Right. So I'll come off the commercial side of things and get back into the technical side of things. So I just want to sort of say, microneedles are being used by the only company I'm sort of aware at the moment who's trying to do this is a company in San Diego called BioLink. And I've obviously read their patent, so I have a good sense that they're putting microneedles into the body and looking at it by electrochemistry. It's probably worth understanding the patent landscape, because there's no point in developing or publishing stuff that's already been patented by a company. So, you know, just be aware of it. there's not many companies that can actually make microneedles. Of course, you know, I would tell you that ZP is one of the few companies that actually can make microneedles. And there are two types of microneedles. You know, there's probably more types, but there's solid microneedles where the microneedle goes through the skin and the enzyme is on the microneedle. And there's also hollow, where the microneedle is a hollow needle and that goes through the skin, but the interstitial fluid then wicks through the hollow and onto a sensor. So the enzyme is not on the needle, it's behind the needle, but the needle itself is hollow. So I read the question like, well, how do I make microneedles? But really the question was, how do I make electronics? But I mean, we do have microneedles on our website. In fact, here's some data here where it's probably 0 millimolar glucose. I think it's 5, 10, 15, and 20. So we have microneedles on the ZP website that are functionalized for glucose, and they work perfectly fine. And we also have electronics, which is called the EZ Flex, that these microneedles will plug into. So this is the electrical connection here, and they connect into this connecting block here. So we do have electronics around how to do microneedles. Oh, sorry, how to do electronics for CGM. Now, this is not the question that was answered, but I am going to answer the actual question. But I just want to put this out there. If anyone, microneedles can be quite expensive to make. You know, if you look on our web store, you'll find, wow, they're expensive. Yeah, they are expensive to make. So I'm quite interested, if anyone in the ZP Developer Zone is interested in having a conversation with us at ZP about actually using 3D printing for making microneedles, I'd be quite interested in that. Like, you know, maybe doing some designs, you try printing them, and, you know, we take it from there kind of thing. The reason I'm interested in that is because, you know, 3D printing is becoming, you know, is becoming more and more widely available, you know, even in university labs. If you can 3D print microneedles, then we have paintable platinum inks, so we can metallize it just using a paintbrush. We have silver chloride that's paintable, so we can put the working electrode down in platinum. We can put the reference electrode down using silver chloride. We have activation formulations, so we have the ability to put the enzyme down onto that platinum electrode. And we also have the barrier layer. This is a layer that goes on top of the enzyme and essentially sort of half protects the enzyme, but also reduces the flux of glucose. So the reason I brought this up is because I think it is quite expensive, microneedles, especially in low volumes. And if there are people interested in out there exploring 3D printing microneedles, then I think I have ideas about how to essentially, I think we would put a 3D printable file on the ZP Developer Zone, allow people to download it, so then they can kind of accelerate their development that way. Because what I'm imagining is we would take one of our PCBs that we have, and then these 3D printed parts could be essentially stuck onto there, and that would make a microneedle array for people trying to do CGM development. In terms of electronics, we do have our own electronics for people doing continuous glucose monitoring. We haven't put this onto the web store yet, but once this is a bit more matured, we'll be putting down this electronics, and I'm going to really try and get the price right down so that it's a very, you know, low cost solution for people trying to do biosensor development. But in the meantime, if you're interested in making your own electronics for CGM applications, then I think there's at least 4 open source potentiostats out there. UWED, the CheapStat, the PSOC, and the DStat. Now, and I will also put a link. You can't see the link at the moment, but I'll put the link under the video. It is something I'll put on the website. But I also want to say that Ahmet, who also comes along to our the webinars, he's been doing, and he's also a member of the Developer Zone. He's been doing his masters on a potentiostat circuit as well. So the real question was, guide me on how to make electronics for CGM, and the answer is there's at least 4 open source potentiostats out there, and we also have a member in the ZP Developer Zone who's also done this. And I also have a suspicion that Aftab, who's also online today, might have done some electronics for sort of potentiostat design. So we've got quite a few people in the developer zone who actually are have an electronics background, know how to design this kind of stuff. And if you're not sure, I'll put a link under the video afterwards, linking back to all these references, and you can sort of take a look at those. Right, so it's 8:29. So let's just summarize up. Question 1 was about how to increase our yield. Unfortunately, yields is increased by effort. There's no magic source. It is also yield is also increased by the environment in which you're working. If you're not working in a controlled environment, if you're not working like we work in a class 7 clean room, using calibrated pipettes, our guys are, wearing face masks, goggles, complete personal protection equipment. If you're not in that kind of environment, then you probably have to accept your yield. My suggestion is don't do electrodeposition of gold nanoparticles. If you're going to use gold, just use a gold electrode. And if you're using a hyper-value carbon electrodes, then there's a nice paper that I've referenced. And then for this one, we've got at least 2 people in the ZP developer zone who have built these open source potentiostats, and I'll also put a link to open source potentiostats underneath the video when we finish. So it's 8:30 and about 59 seconds. So yeah, that's the ZP developer zone for this week. Sorry I talk fast, but I do appreciate it. I see a lot of the regulars, let's say. So Ali's here, Aftab's here, Hicham is here, Philippe is here. I've noticed Philippe, you've been coming recently, so thank you. Dimaz, haven't seen you, but Dimaz has been one of our oldest time members, and Hayun, it's nice to have you along. So thanks guys, I'll say goodbye now, and don't forget we will be here 8 AM next week as well. Okay, and post your questions in the forum, and happy to at least give you an opinion. And if anyone's interested in 3D printing microneedles, give me a shout in the forum, and we'll see if we can do something about it.